Okay, so your next module is PWM modulator, and we already know what PWM modulator does. Takes your reference, if this is your V control, and this is your VRAM. Okay. So what you need? You need RAM generator, and comparator. So these two modules you require, or so if already have the clock, then you can generate RAM from that. If you don't have the clock, then you need an oscillator. So you can design the oscillator itself to give you the RAM directly. Okay. So let's see how RAM generator looks like. So one simple way we talk about, you just need this. CRAM, and if you already have the clock, you can generate the reset signal at the positive edge of your clock. So this will be nothing but reset, and this is your VRAM. I call it IRAM. TSW. So from here you can find the, so if this is going from 0 to, let's say, VM. So what will be the VM? C VRAM over TSW. Okay. C is actually CRAM. So from here, and VRAM is actually VM. Correct? IRAM TSW over CRAM, or you can write IRAM into FSW. Correct? So CRAM and IRAM ratio will control your VM. FSW is, once you fix it, then you can choose IRAM, CRAM. So smaller the CRAM, then smaller current you will require. So, but one thing you have to look into, this is going at the input of your comparator. So don't make it order of like femtofarad, so that parasitic will kill it. Okay. So make sure that whatever the parasitics are at VRAM node, they should be very small portion of your actual cap you are putting, and that's why we choose order of picofarad 1 to 10. 1 to 10 picofarad kind of. 10 picofarad is even much larger side, but 1 picofarad should be okay. Okay, so based on that you choose the current. No, whatever the pulse width of this, you have to make sure that the switch should be able to discharge to 0 within that time, and that will be the reset time. If you are looking for your PWM only controlled by this RAM, then this reset should be very small portion of that. So, if let us say I am talking about 1 megahertz or so, which is 1000 nanosecond, then usually we keep this reset time order of 1 nanosecond also, so that it should not affect your PWM, because we are looking at single edge. If you make this slower, then it will look like a dual edge modulation, then your behavior will change in that case. Okay. So, this is your leading edge, trailing edge. Now, let us see if I am not given the clock. So, we do not have the clock, then how can we do this? We have to design the oscillator. So, let us see. So, have the same thing. IRAM, CRAM, now let us say this is VM. So, what would happen when this switch is off, this reset switch is off, this current will charge your VRAM, and the moment this VRAM goes above VM, this comparator will pull the gate high and it will reset, and as soon as it gets reset, what will be the state of the comparator output? Will low. So, this switch will automatically turn off. So, your reset time will depend on the delay of this comparator. Okay. So, which means if your delay keep 1 or 2 nanosecond, that will become your reset time. So, based on your reset time you require, you have to design this comparator according to that. Okay. So, let us say if TD is the delay, then this will become TD. This is your reset signal, and this will become the ramp, and that is what we require. In the whole converter, you only require ramp, you are not looking for any square wave clock. But what if I need a square wave clock, then can I get from here? Because the comparator output is has a very narrow pulse width. Yeah, one way, like, okay, just have a VM by 2 and you will get a 50% duty cycle of that. Other way is you run it at 2x and put a divide by 2 at the output flip flop, it will give you 50% duty cycle. Okay, understand or not? So, if you have this, and if I pass it divide by 2 clock divider, which is nothing but Okay, so it will toggle at every edge. You can use T flip flop. It's just a counter, huh? Divide by 2 when you say divide by 4, modulo 2, modulo 4, that's a counter. Okay, so the output of your flip flop will be half of this frequency, but 50% duty cycle. So this is, if this is FSW, this will be FSW by 2, which means if I want FSW, then I have to run it at 2x frequency. That's it. Or other way could be, you just take the VRAM, compare with VM by 2, and you get 50% clock output at the same frequency. Okay. So, the advantage here is, let us say if your current is changing here, it will only affect your frequency, but VM will always remain constant here, because you are comparing with the comparator. But in this case, if the current changes, your VM will change, or the capacitor changes, your VM will change, because your frequency is fixed here. So, if you change current or capacitor or both, one has to change, whether VM or frequency, but we are forcing the switching frequency here. So, VM has to change. Here we are not forcing the frequency, but we are forcing VM. So, switching frequency has to change. So, this was a trailing edge. How do we do leading edge? Let us say I want to do a leading edge. Yeah, PMOS, and you set it. And you will discharge let us say this is VDD, this is your leading edge. Reset. So, now in this case your reset will be like this, because it is a PMOS. So, just the inverted signal of what we had for NMOS. So, this is your VM, this is your VDD, and this will go to VDD minus VM. Okay. So, for dual edge, and if you want to do the oscillator, you can do the same way. Just connect that PMOS, and with the comparator will now reset, and the waveform you get at a VRAM will be exactly like this. Dual edge. How do we do the dual edge? You mean the reset time? But that is uncontrolled. No, but then the slew rate will depend on the MOSFET resistance. So, you are charging with the current and discharging with the, so there is a mismatch in the two. If you are charging with the current, you want to discharge with the current, and now you are discharging with the through a resistor. So, it will have exponential behavior, it will not be linear. So, non-linearity will also be there, until it is a very small signal. For a small signal is fine, but large signal, for a small signal I mean if you are looking for a small signal, for a small VM, let's say I would say approximately or less than 1/10 of VDD. This is good enough, huh? RC, use clock signal which has TSW. You get a perfect triangular wave here at the output. If this is your VM. But when the moment you start increasing the VM, you will see exponential behavior, non-relative will come and your loop gain will not have the same relationship. 1 over VM now will become something else, the gain, modulator gain. So, you need a charge and discharge both currents. Okay. So, IRAM this is your capacitor. Let us say I have NMOS here, VDD, ground. So, if I give a clock signal here, what will happen? Both are IRAM. When the clock is high, it will discharge. When the clock is low, it will charge. So, you will get a charge discharge, same thing. But is there any problem? I mean, will it happen the same? KCL? What KCL?
If we switch off the, for example, we switch off the NMOS, then current will increase the voltage.
No, but you are charging for a limited period, huh?
Yeah, but if one of them gets switched off, then the current that is going into it or getting withdrawn from it, where it will go?
It's going to the capacitor, huh?
So, for example, if PMOS is on, then
When the PMOS is on, so let's say you have two labels, okay, Vmax, Vmin. So, when it goes to Vmax, your NMOS is turned on, PMOS is off, so it will discharge. When it goes to Vmin, it will charge.
yeah, but those IRAM, the current sources will be at that. These are not ideal current sources, so if one of them.
No, so that's what I am asking. What is the problem? You are not able to define properly what the problem is. Rise time fault. Who will define the rise fall here? Clock? No, clock is perfect 50% duty cycle. Your on and off time are perfectly matched.
From 0 to VDD, the time taken transition. It should be in such a way such that either the top switch conducts or the bottom switch conducts.
It is like
No, that's not a problem. The problem is the mismatch between the currents. If you have a mismatch between the current, let us say delta I, and delta I you are dumping into a capacitor or drawing or charging the capacitor. So, you are integrating delta I, plus or minus delta I. So, it will integrate and saturate. It will either go to 0 or go to VDD, because you have an integrator. Your capacitor is nothing but integrator, it is a current integrator. So, any mismatch between these currents will get integrated and will saturate your output. Okay. So, and we cannot perfectly match. I mean, if you can match, then that won't be a problem, but that is impossible. Even if you have a, let us say I mean, these let us say 1 amp of 1 microamp current, and even if you have a 1 nanoamp mismatch, that may get integrated, even though it will take long time to saturate, but it will saturate, maybe after few seconds it may happen. Any mismatch between top and bottom currents will get integrated and so this doesn't work. So what do I need to do?
You do have single IRAM
Single? But how will you discharge then?
some logic can change its path.
Go back to your oscillator. Huh? What was the oscillator doing? What was limiting in the oscillator? What are we limiting here in the output ramp? Voltage, huh? So you can limit high and low voltage. That's it. It will never saturate. You need two comparators here. If this is, let's say, Vref H and okay, lower threshold and upper threshold. So when this goes below set reset, let's see. This is CRAM. I need two currents here. So let's say PMOS and current. VDD. Okay, so let's see who will control what. This is VRAM. So we know if this VRAM goes above, if this VRAM goes above Vref H, we want to discharge. Which means this should control your RST and I will call it RSTP. So let's say I have a Q and Q bar. So which should be RSTP and which should be RSTN? Q bar should be RSTN. But it's a P and N MOS, ultimately they should be driven from the same signal. Okay, so which one should be? I mean, you can use separate, put an inverter and you can separate signal, that's fine. If your switches are of the same type, then it has to be driven with a complementary. Okay, so which signal should drive the reset? So now let me call it reset. Q or Q bar? So when this goes high, it will reset and this should start discharging. So this will be your reset. Now apply the logic. Check both the sides, high and low. So then it will start discharging, the PMOS will turn off. So when this goes high, it will reset. When it gets reset, what would happen? Q will go low, this will go high. So this will turn on, this will turn off. So it will start discharging. Okay, when you are discharging this guy, what would happen to this? This will go low. Okay, because we only want a glitches here. Otherwise, or a condition where R and S could be 0 0, but they cannot be 1 1. That is not allowed. So now let us say if discharging and it goes below this VRFL, what will happen? This will go high. Okay, this goes high, this will set. So reset will go low. So reset goes high means this NMOS reset goes low, NMOS will turn off and PMOS will turn on. Okay, now it will start charging again. So both the comparators will only see the glitch during transition time. So which means R and S most of the time will remain 0 0, and you will see a triangular wave here. And what will be the output at reset? Not impulse, in this case it will be a square wave. This will be your TSW and your VRAM will be like this. Oh, sorry. So in one period you should get the complete . Okay, so this is your VRAM. And what will be the amplitude of this? VREF H minus VREF L, which means the difference, if we keep it equal to VM, it will remain VM. So how do we decide? How do we choose VREF H and VREF L? Can anybody tell? I mean, can I keep, let us say, VREF L 0 and VREF H 1 volt?
Whatever the range of control voltage.
So how do you define range of control voltage?
VDD by 2 plus minus delta.
Yeah, so what you want, your error amplifier output is nothing but your control voltage. Okay, so this is your output stage of your op amp. Okay, I am just drawing the second stage of error amplifier. So it has some VD set VD set, and this also requires some, so VD set P and VD set N. So even if it, let us say 100 millivolt, you can go as low as 100 millivolt, or on the higher side you can go as high as VDD minus 100 millivolt. But the problem is one will be in the deeper saturation compared to other, but ideally you want both should be in the deep saturation. So you always keep the common mode of your RAM at VDD by 2, then you get a full range in both the directions. So this is your VCTRL, and if this is my VRAM, then we try to keep it VDD by 2. So if I want VM equal to 1 volt, then I will keep Vref L equal to how much? So if my VDD is, let us say 1.8 volt and I want 1 volt VM, so this should be 0.4 volt, and this should be Vref H equal to 1.4 volt. So minimum you get 400 millivolt for NFET and 400 millivolt for PFET. So even when you are operating at a lowest duty cycle or max duty cycle, let us say close to 0% or close to 100%, both the devices you ensure are in deep saturation. Otherwise what would happen? Your gain will drop. So your loop gain behavior, whatever you have, I mean your UGB may drop or anything may happen. Your DC gain has dropped, so, and you may even get a large output error if you are operating near 0% or 100% duty cycle. So keeping common mode voltage of ensures enough headroom for both NMOS and PMOS to keep them in entire duty cycle. Zero to 100%. Okay. So, or simply you can say that if this is VDD by 2, then this will be how much? VDD plus VM by 2, VDD plus VM by 2, and this will be VDD minus VM by 2. So you are getting 0.8 by 2, which is 0.4. Okay.